Today, in this period, I talk about the instrumentation. So already you use the Raman microscope and ATRI, FTIR, and you have some experience about vibration spectroscopy. And there is some description. This talk is about some description about each component in the Raman spectrometer. Okay, so this is the development so far. So in 1921, C.V. Raman experiments on the color of the sea, showing that color was due to molecular diffraction. And in 1928, Raman and Krishnan discovered the Raman effect, and he was laureated a Physics Nobel Prize in 1913. At that time, he used these instruments. This is Raman's spectrograph, and you can find in Kolkata. I want to visit there, but I had no chance for this time. And you have probably many times as far as you are in India, so please visit and see it. Okay? Then, after the finding of the Raman effect, several apparatus has been developed. One is a monochrometer. In 1960s, lasers were used as a light source for Raman spectrometers. Also, in 1980s, CCD detectors were used for Raman spectroscopy for the first time in 1979. Okay? So, I cannot cover all of the topic about the development history of the Raman spectroscopy. So, there is other important keywords. But today, I talk about instruments. Okay? So, this is the least necessary component for the Raman spectroscopy. So, we need light source, sample cell. Then, probably we need a focal length around here. Then, Raman scattering is generated. Then, we collect with this lens. Then, the diverging light becomes parallel. Then, this beam is focused onto the monochrometer entrance slit. And Rayleigh line or light source wavelength itself is cut by the filter. Then mixture of the colors in the scattered light is monochromated and detected. So here is a figure of the kind of smallest setup of the Raman spectroscopy. This is a laser. This is a monochrometer. This is a sample cuvette. Okay, laser beam passes through the optical fiber and irradiates a sample, and the scattered light is collected and delivered to the monochrometer, and monochromated detected. Okay, recently such a small, very convenient tool is available. But anyway, the principle is the same. So we need some parts, light source, sample cell, filter, monochrometer, detector. So let's think about these components. Okay, in order to generate Raman signal, what kind of light source is suitable? What kind of light source can we use? Sunlight, or lamp, or laser? Okay, we know sunlight intensity is high enough, and wavelength is continuous, but stability is unknown. Lamp intensity is moderate, wavelength continuous, stability is good. And laser intensity is high, very high, we are always watching laser from the side. If we watch from this direction, our naked eye will be damaged and does not recover. Very strong light. Wavelength is single. Stability is very nice. If we use a continuous light as a light source of the Raman scattering, what happens? Raman signal occurs at certain position energetically apart from the excitation light. So, for example, let's consider 1000 wave number. If this is monochromated single wavelength, distance from this wavelength 1000 wave number is only 1. But if this is various, then 1000 wave number apart from this wavelength is also various. Accordingly, the Raman band becomes very broad. So it's not worth discussing, or we cannot discuss such a broad peak. So it's preferable feature that laser has a single wavelength. By using this, we can get single Raman line. So how can we generate a laser line? To consider that point, let's start from the Boltzmann distribution. Here there are two energy levels, and the population is N1 and N2. At any temperature, always N1 is larger than N2, as far as N2 is energetically high. And the population ratio is the function of the energy difference over kT. This is the Boltzmann distribution. Okay? Then light comes again. Light comes, then light is absorbed by these two particles and its intensity becomes lower. This is the absorption process. But even in that case, the population on the ground state, lower state, is larger than upper state. And if the inverted population realizes, that is, if the population in the upper state is larger than the lower state, then when we irradiate the light, then the induced emission process takes place. That is, this light drives molecule from upper to lower state. And this energy difference is changed to light. Accordingly, if in the case we can realize the inverted population and irradiate the light, it drives two particles, for example, and light intensity is intensified. Okay, this is the absorption process, and this is the induced emission process. So if we irradiate the light to this system, light intensity becomes weaker. In this case, light intensity becomes larger. So this is light absorption. On the other hand, this process is light amplification by stimulated emission. This light stimulates a molecule to move from top to bottom. And the laser is the abbreviation of light amplification by stimulated emission of radiation. Okay, so in the laser box, the inverted population is achieved, and light is irradiated to inverted population. Then this light becomes intensified. By go and back, this laser intensity becomes much larger. But the population ratio is always obeys the Boltzmann distribution, so it looks difficult to achieve inverted population. To circumvent this situation, they prepare some laser medium. In the laser medium having specific electronic structures, inverted population is achieved. For this purpose, an external energy source is required. If there is no external energy source, all the population is in the ground state. But by illuminating some light to this system, this population is pumped to upper state. Okay? If this system is left as it is, it should return to original position immediately. But in this special laser medium, this population does not return, instead go to sub-state. Okay, so it stays here. It is pumped, then moved to upper state. Okay? Then you see upper state population is larger than the lower state due to the external energy source. Then by illuminating this inverted population by light amplification becomes possible. This is also the same. Due to the external energy source, inverted population is realized. Generally, there are two kinds of the laser medium: 3-state laser and 4-state laser. In this case, 3-state, first, second, third. Then the laser emission occurs from the second, first, second, third. So laser emission occurs between first and third state. In the case of 4-state laser, first, second, third, fourth. In this case, the population of the lower state is 0. And laser emission occurs between 3rd and 4th state. So this is more efficient amplification is possible. Okay, in the real laser, this laser medium, including N1 and N2 inverted population, is flanked by two mirrors. Left mirror is nearly 40 to 70% reflection, 30 to 60% transmission. Right hand side mirror almost 100% reflects the light. Then here is the inverted population. Light comes in. Then it becomes stronger. And by external energy source, it is populated to upper state again. Then this is reflected, so light stays in this cavity mirror pair. So go and back, okay, go and back. During this process, the light passes through laser medium repeatedly, and the intensity of light becomes larger and larger. So it's possible to get a high energy light that directs one direction. Okay, this is the principle of the laser emission. There are several kinds of laser. Diode laser, diode pumped solid-state laser pumped by flash lamp, or gas laser pumped by discharge. Okay, in the case of diode laser, here is some diode. Then current excites this diode. Then it emits a light. And this emission light is laser light. In this case, the electricity is the external energy source. Also, this light is also available as an external energy source of the laser crystal, laser medium. So by making a cavity that flanks laser crystal and irradiate the light from outside, then this light realizes the inverted population in this laser crystal. Then light goes back in this cavity and emits the laser light. Another way is to pump the laser medium by flash lamp. Okay, so flash lamp is in this case external energy source. By illuminating laser crystal, they make the inverted population here. Then here is a cavity. Then laser emission occurs. The fourth kind is a gas laser. So this is typically helium neon or argon ion is packed with this container, and the end is mirror. And these gases are excited by discharge. Then it goes to excited state, and the energy of the molecule is turned to energy of light. So by going back this cavity, and laser intensity becomes strong, then it emits the laser light. Okay? So yesterday you saw the lasers near the Raman microscope. It was so compact, so I guess it is classified to this group. Okay, this is much smaller than the diode pumped solid-state laser, and this is huge. This is also huge, a few meters. And recently, this kind of laser is widely used for Raman spectroscopy because it is almost maintenance-free. Okay, turn on the key switch and wait, then laser emission occurs. Very convenient. When you purchase lasers, please check the specification. Okay, I list here 532 nanometer laser. 532 nanometer. This is also 532 nanometer. Price is different. Why? Cheaper is better? Maybe no. Okay. Difference of the price may be related to maximum laser power. In this case, 100 milliwatt, 100 to 300 milliwatt, 200 milliwatt. Okay, also the price is related to line width, energy width of the laser line. Narrower is better for the Raman spectroscopy. So 532 nanometer correspond to 18,797 wave number. If you purchase the laser having the width of 1 nanometer, 532 plus minus 1 nanometer, it means energy bandwidth is 35 wave number. So Rayleigh line has width. Accordingly, Raman signal has a width. It is inevitable to detect broad Raman line. This is not convenient. We cannot discuss peak shift as small as 1 wave number. So 35 nanometer width originates from the laser source. And 532 plus minus 0.1 nanometer, this is okay for the Raman spectroscopy. In this case, energy error in the energy is 3.5 wave number. Typically, we do the Raman spectroscopy with resolution of 8 wave number or 10 wave number. So 3.5 is smaller than that value. When you purchase such a very nice one, spectral line width is 1 kilohertz. Okay, 1 kilohertz looks different from wave number, but this is a wave number in 1 centimeter, and it is convertible with the unit frequency hertz. Number of waves in 1 second. This is in 1 centimeter. Okay, so it's convertible. If I convert kilohertz to wave number, it corresponds to 3 by 10 to the minus 8 power centimeter inverse. So this is extremely pure green light. Sometimes this is necessary for certain experiment, high resolution measurement or something. But as the parameter becomes better, price becomes better. So please choose according to your purpose. I don't recommend such a broad laser line. So these two should be taken into account. Also, beam pattern should be TEM00. Please make sure. TEM00 is this type. There are several patterns, and if you choose TEM00, intensity distribution along x-axis is Gaussian, y-axis Gaussian. So center is the strongest. That is, energy of the light can be accumulated at the center. This is very good property for the Raman spectroscopy. So please check several parameters when you choose. And laser has two output patterns. One is a continuous wave. The other is a pulse laser. Continuous wave laser output same intensity along with the time. Pulse laser flashes short time and become dark. Wait. Flash is some time and become dark. Wait. So this is the pulse flash lamp. When we set the average power 1 milliwatt, then this height is 1 milliwatt. On the other hand, in the case of pulse laser, most of the time it is dark. Very limited time it becomes shiny. Accordingly, this height is more than 1 milliwatt. When we consider the pulse width is 10 picosecond, repetition rate is 1 kHz, then the pulse energy per joule is calculated by 1 milliwatt multiplied by 1 second divided by 1 kHz. So 1 milliwatt, 1000 pulses. Then 1 milliwatt by 1 second, 1 millijoule per 1000 pulse. So 1 pulse corresponds to 1 microjoule. Then 1 microjoule pulse flashes only in 10 picosecond. So divide by 10 picosecond, and we get this value. So average power may be 1 milliwatt, but in this case 100 kilowatt. Okay? So pulse laser achieves very high laser intensity in a short time. So usually we choose CW laser for the Raman spectroscopy because it damages the sample. And this is mild, does not damage the sample. So, and more importantly, this is much cheaper than the pulse laser. So if the purpose is only the Raman spectroscopy, let's choose CW laser. Okay. I should explain this page. So, how can we prepare the pulse laser? Okay, one method is the Q switching. So, put some gate in the cavity and open the cavity for a short time. Then, during the opening time, laser goes to the output, so it becomes pulse. Long time, the light does not come out. When the gate opens, light comes out. So this is Q switching. Okay, so by opening the Q switch, we can get a giant pulse, large pulse signal. Okay. Another method to achieve the pulse is mode locking. It's interesting when we overlap many wavelengths, what happens? Okay, this is my calculation. I added cosine function by changing j from 10 to certain number. If I combine the cosine function from j equal 10 to 20, then the appearance is something like this. Cosine function oscillates. If I sum up to 30, some beat start to appear. 60, 110, 210, 510, 1010. By overlapping many cosine functions, it becomes such a shape. As a consequence of the interference of the multiple colors, multiple waves, the electric field cancels in this region and has a large value in only limited time. So if we can prepare laser beam having such a large number of wavelengths, we can prepare such a pulse laser. And this kind of mode locking is achieved by using the titanium sapphire as a laser medium. Already this is commercially available and widely used and very stable. Maintenance is much easier than the other system as a pulse laser. Q-switch laser is sometimes unstable and sometimes due to the power cut or something, system shut down. So it's trouble is sometimes occurs. But mode locked pulse laser owes its performance to the laser rod, so always it's stable. So that's why it is mode locking laser, pulse laser is widely used nowadays. So in order to measure Raman spectroscopy, we need the light source. I explained the laser system. Second is the sample cell. There are many kinds of sample cells, capillary glass or put on glass plate or rotation cell. We may prepare such a nozzle and push from this side, then liquid plate is formed here. So without window, we can prepare the thin liquid film. This is liquid jet. Or we may prepare 2 wires, then form the liquid film between 2 wires. This is also the windowless system. We can prepare the thin liquid film. It's convenient for Raman spectroscopy. If we use this kind of round bottom cell, then it is advantageous to improve to get a larger signal. So this is capillary. And refraction occurs at the interface of the glass and air. So even if we prepare a large numerical aperture lens, only limited number of limited solid angles can be covered by this lens. If we use round lens, this kind of reflection does not occur, it goes straight because it's normal. Then we can cover larger range with the same lens. So it's advantageous. Someone makes round hole on the metal surface and fill this semisphere with the sample. Then scattered light can be collected by lens. And scattered light onto the bottom is reflected by this curvature and returned to surface. So this is also useful to enhance the signal intensity. Besides, there is a method to utilize the total reflection of the light. Okay? Typically, this or this are the most convenient. In the case of resonance Raman spectroscopy, the sample is damaged, so rotation cell is used, and always fresh sample is supplied onto the focal point. Then sample damage can be avoided. The third, we need to put a filter to cut the Rayleigh line. Sometimes we use filter in front of the laser source to purify the laser light. Okay, if some laser emission line includes some satellite lines, they are not necessary. So let's put a filter and cut these unnecessary lines. This is bandpass filter, only passes 633 nanometer. Okay? Then purified 633 nanometer is irradiated to sample cell. But when we deliver the signal into the monochrometer, 633 is not necessary anymore. It's Rayleigh line. So let's cut 633 by using band elimination filter or not so-called notch filter. We may use long pass filter also. So some kinds of filters are necessary to achieve good Raman measurement. Okay? There are many bandpass filters to purify laser output. The most cheapest one is colored glass filter, $32. But this is typically used for the fluorescence, not for Raman. So this is not available for the Raman spectroscopy. Okay, bandwidth is so broad, so even if I want to use only 633 nanometer, many other lines cannot be cut. If the bandwidth of the transmission region is plus minus 2.1 nanometer, prices become 10 times larger, $425. Okay, this is, I'm not satisfied with this. I want to make it narrower. Price is $753. Okay? And I explained, in the case we want to measure the low frequency Raman spectrum, then such a small width is necessary. And I could not check the price of this product, but I'm sure it's highly expensive, more than this filter. Okay, so filter is necessary, but please consider your purpose. If your purpose is not low frequency Raman, such a nice one is not necessary. It's also the case for the notch filter. And previous one is a bandpass filter. This is a notch filter. So please visit the website of the maker of the filter. You will find many filters. Okay. Price is 385 or 1045 or 710. So this is a filter for 532, and cut off is 455 wave number. So Rayleigh line is here. We want to cut the Rayleigh line. Then width is rather broad. That is, we cannot detect the Raman lines below 458 wave number. In this case, this is 90. It's much better. We can detect Raman lines in this region. This is 186 and the price is moderate. Okay, so checkpoint is cut off wavelength when you choose a filter. So please make sure your purpose which peak you want to focus on. If you want to detect all the peaks, range should be wider. If your interest is nearly between 1000 to 2000, then such a nice one is not necessary. It depends. Okay, so for the measurement of the Raman signal, light source laser is needed, sample cell is needed, filter is needed. One of the most important elements is the monochrometer. This is an instrument to separate mixed colors into each wavelength. That is to monochromate. Okay. Literally, this is the black box. Inside is quite black to suppress the stray light. But we should know what is inside. In the black box, there is a mirrors and grating. Okay. According to the configuration of the mirror and grating, there are several types: Tselony-Turner, crossed Tselony-Turner, Littrow, or Seiya-Namioka. So, among them, Tselony-Turner is recently the most standard style. So, pathway is M shape. Okay, you may check what is a Littrow, what is a Seiya-Namioka. So, advantage of the Littrow is that all the system can be compact. Seiya-Namioka style, there is no mirror. So this is a curved grating, and entrance slit light irradiates a curved grating and automatically focus on the exit slit. So the number of the optical element is fewer. And again, this is compact and throughput is high. But this is the most widely used style, Tselony-Turner. Okay. In this figure, A is the incident beam, B is the entrance slit, C is a collimator. So always we put the lens and focus Raman scattering light onto entrance slit. So the size is the smallest at this point. So it converges. After that, it diverges. This collimator makes it parallel beam. This is curved mirror. Then parallel beam is irradiated onto the grating. Then this element makes each color propagating to the different direction. Then each color is focused on the exit slit. If we put exit slit, only a selected color can pass this slit. Instead, we may put detector at this position, at this plane. Then we can detect which color has what intensity using this setup. When we use monochrometers, there are several important parameters. Focal length, f, that is the distance between the slit and collimator. Second is large f number. This is calculated by dividing f by diameter d. So this parameter is related to the maximum angle of incidence. The third is the reciprocal linear dispersion of the grating. I explain this later. Fourth is the brace angle, brace wavelength. This is also the parameter of the grating. So the ability of the monochrometer largely depends on the ability of the grating or dispersive element. So they are important parameters. Okay. Again, the grating is a monochromating optics. It differentiates the propagation direction of light depending on the wavelength lambda. Okay, you may look at a CD or DVD and it is colorful. The principle is the same. On the surface of DVD there is a small groove and it serves as a diffraction element like grating. So appearance is similar. White light is separated by its color. Do you know what is the principle of the grating? Can I skip or shall I explain? Okay, on the surface of the grating there is a small pattern of which the spacing d is smaller than the wavelength. In the presence of such a tiny pattern, incident light is diffracted. This is in contrast to the mirror. If this is flat surface, reflection occurs. But if there is a very small pattern, spacing is less than wavelength, the diffraction occurs. It does not go necessarily reflected. Okay, so this figure is about only one ray, but actually there is And so parallel beam comes onto the grating. So there are multiple rays and multiple diffraction lights. If the diffracted light constructively interfere with each other, then it can propagate to a certain direction. So unless the constructive interference, it cancels due to negative interference. So the light goes along the limited or selected direction. Okay, it may be better to check this document again. Diffraction occurs when the small dot is allocated with a distance d less than wavelength lambda. Then light comes in with the angle with respect to the normal. Then the diffraction occurs. Okay, diffraction occurs to all the directions. But let's pick up the component having the angle beta. Beta is again counted from the normal to the surface. When we consider two incident rays, then there occurs two light having in the beta direction. Difference in path length is given by CA plus AD. CA is this distance, AD is this distance. So this length is excess traveling distance between for this ray in comparison to the first ray. And CA plus AD is given is equal to d sine alpha plus sine beta. If this excess, if this excess distance is m times of lambda, then positive constructive interference takes place. If m is equal to 0, then it is a mirror-like reflection. There is no lambda dependence. If m is equal to 1, it propagates to a certain direction. This is so-called first-order diffraction. If m is equal to, this is second-order diffraction. Okay, so constructive interference of the diffractive light. Constructive diffraction, constructive interference of the diffraction light is achieved when it satisfies this equation, or excess traveling distance is m times of lambda. Okay, this is a diffraction condition. And we move to the structure of the monochrometer. Let us use n instead of d. Okay, so far we counted the distance between two patterns, tiny pattern, by using the distance d. But let's use its inverse n, number of structures per millimeter. Then d and n is inverse of d, so equation 1 becomes sine alpha plus sine beta is equal to nm lambda. D is replaced by n. By differentiating with beta about left hand side and lambda about right hand side, we get d beta d lambda is equal to nm per cosine beta. Okay. Multiply by this equation by f focal length f, then it becomes f d beta d lambda is equal to f nm over cosine beta. We want to know how largely two colors are separated at exit slit. This is the performance of the monochrometer. So let's call this axis x. And calculate distance of two colors on this plane. That is dx. Then dx is calculated by considering the radius f and small angle d beta. So there is a relationship dx is equal to f d beta. Then this equation becomes d lambda dx is equal to cosine beta over nmf. D lambda dx is difference of the wavelength in a unit length along with x-axis. So this is a resolving power of the monochrometer. So the power of the grating is represented by this parameter. This is so-called reciprocal linear dispersion. Okay, in other words, this is monochromating ability, how strongly it can separate two colors. So from this equation we see if the f is larger or monochrometer is long, then resolution becomes higher. Different color can be separated further. If the f is small, then different color comes across. In other words, the limited area of the detector covers wider spectral range. Again, it depends on your purpose. If you want to separate two peaks very nicely, please choose larger monochrometer with larger f focal length. If you want to measure the whole spectrum at once, then please choose small f monochrometer. It covers wider region. Okay? This is the explanation of the blaze angle. Okay, I explained on the surface of the grating there is tiny patterns But actually, in your setup, grating surface is such a serrated pattern. Okay, like a saw. Then you can imagine incident light comes in. If the diffraction direction is mirror image with respect to the normal, if this angle and this angle is the same, then it is like a reflection, and the efficiency should be higher. Intense diffraction occurs when the direction of the incident light and the diffracted light are the mirror image. Okay? And the angle of this pattern is so-called brace angle theta b. This condition is satisfied if alpha and beta, that is defined to the normal to the whole grating surface. This is alpha, this is beta. If alpha plus beta is twice of the theta b, then this condition is satisfied. But beta is the function of lambda. So this condition is not satisfied always. The equation 6 should hold on the particular wavelengths theta b, because the angles alpha and beta are the function of lambda. So from equation 2 in the previous page, nm lambda is equal to sine alpha plus sine theta, sine beta, and it is converted to this form. Then substituting this relationship into here, we get this equation nm lambda b is equal to 2 sine theta b cosine alpha minus theta b. Then from this equation, we can calculate special wavelength lambda b that is special for this grating by using angle theta b and the number of grooves per millimeter n. This special wavelength that satisfies this condition is so-called brace wavelength. In other words, the highest performance of this grating is achieved at lambda b, brace wavelength. The diffraction efficiency of the grating is the highest at the brace wavelength lambda b. So lambda b designates the character of each grating. So when you have a chance to order grating, please check brace wavelength. That product is optimized for this wavelength. Okay, so if you want to measure 266 nanometer, do not purchase brace wavelengths of 1000 nanometer or so. So closer wavelength, please choose the grating having the nearer, closer brace wavelengths. It's better. It promises better performance for your condition. Maybe it's a time. Just a moment. So probably this is close to the last. And when we set up the monochrometer, important step is F matching. Okay? So the angle that this monochromator can receive is determined by this diameter d and this length f. So this angle parameter related to this angle is given by given as f number f over d. On the other hand, focal length spec of the focal length is defined by numerical aperture NA is equal to diameter d over 2 by focal length. Okay, considering these two parameters, there is a relationship. Considering these parameters, incident beam is 100% delivered to the detector when this equation is satisfied. So, converging angle determined by this lens and diverging angle covered by this mirror should be identical. Then the performance incident light is 100% utilized and delivered to the detector. Okay, this is an example. If you choose too small lens or NA is too small, then light passes through this angle and it is introduced to monochromator, but only white part is used. Only limited part of the this mirror is used. Monochromator is not fully utilized. Okay, this is a loss of the performance, so we should set F number, NA number large. Let's make it larger. If you set NA too large, what happens? Okay, for this time, some fraction cannot be covered by this mirror. In this case, the incident light is not fully utilized. So when you purchase the monochromator and construct a Raman spectrometer, please check these parameters and please order proper focal length. Then the performance becomes best. Okay? This is the last page. Okay, detector. Yesterday I explained they use a CCD detector in the Raman microscope. And at that time I explained CCD detector is the instrument to convert a photon to electron and digitize and make data. At that time I explained conversion efficiency of the photon to electron is nearly 80%, but I remember this figure. Long time ago I prepared this figure. Efficiency is close to 96%, 97%. Okay, so technology is improving always, and the conversion efficiency is close to 100% at limited wavelengths. Okay, so when you purchase the detector, please check the sensitivity curve. Depending on the coating of the optics or glass, window glass, or some parts, efficiency may be highest at 800 to 1000 nanometer, or in this case, efficiency is highest at 500 to 700 nanometers, or by adding some coating, efficiency at the UV region becomes improved. So please choose proper detector for your purpose. Okay? And one more important parameter is the noise level. So each detector has their own noise level. So one of the parameters that represents an S ratio is a D star. But there are many parameters. I cannot cover all the parameters, so it's better to not to explain only this parameter. So please check dark current or some thermal noise level, or many parameters are important to evaluate what is the noise level. So please check what is the signal intensity and what is the noise level when you order detectors. Okay, and this is all for my talk. Okay, this is all.
If you have any query, please ask. Anybody has any query? So beauty of this research person is that they not only of the system, they themselves construct the instrument. So they know what is the purpose of which parts and which is how to construct the instrument. So it is a unique personality, and mainly it is in this kind of developed country people. They construct the instrument by assemble different parts, and then they use that one for getting some fundamental result, optimizing condition, and then they use it for application purpose. So it is like a big area they cover, each and every individual. So that is a good thing with Hamaguchi lab. He belongs to that lab where everybody was busy in constructing. They modify the instrument, they buy the detector themselves. Even in you will be having another lecture on Monday, Professor Koichi Ota. I sent you the mail, BHU student, you might have got Monday. He is another wonderful who makes instrument. He is senior of both of us. So he also, they purchase the instrument parts like detector, monochromator, lenses, lasers, and then they construct the whole instrument. And mostly the instrument they construct, that performance is superior than whatever we purchase spending lots of money. I think it is correct, no? So whatever instrument that you construct, and their resolution and other things are better than commercially available instruments. Often they tell it. So it's a very nice thing. So whatever you are listening, the explanation of the parts is not just he's reading it and collecting it from the internet and giving you the lecture. It is this part of their activities. So I'm really happy that we could have such person. So if you already have some background, then you could have a very, very nice discussion. They know lots of things regarding this instrumentation. So thank you very much for your patience till 6 o'clock. you are have so much patience that very nicely you are explaining to our students, and really we are thankful for your presence for almost 7 days here and leaving his own work just to come and teach us. So I am thankful on behalf of means organizing committee as well as on behalf of GAN National Working Committee. I want to express my gratitude to you for coming over here, giving all the lectures, and even with additional times you have given on us. So thank you very much, and we wish that we will be seeing you again. Thank you very much.